Hi everyone, I'm Zhulien and I'm going to talk to you about recursive string diagrams. It's not really compilation, there's some compilation, but whatever. Okay, so let's start. So why did we do this? So this is joint work with my supervisor Aleks, who's going to speak after this. So there's this thing called the ZX calculus. I don't know who's just heard of it. Yeah? Okay. Also, I was going to ask, do you like category theory? Raise your hand. Okay. This is just for... So, okay, doesn't matter. So this is a graphical language for quantum computation. The only thing I'm going to point out about this is the wires here are single qubits, okay? That's all you need to know. Next thing, so there's an extension called the scalable ZX calculus, because like diagrams in ZX tend to kind of become very, very large and they're unwieldy. So in here, the bold wires are registers, so you have a register of qubits. And the thing I want to point out is this thing here called dividers and gatherers. So you can peel wires out of a register, so it's fan in, fan out, and fan in basically, and you can gather them back up. Okay, so we started thinking about the scalable ZX calculus, and we wanted to do kind of a QFT in scalable ZX because they have this looping construct, but then it was a bit difficult, and then we said, what about recursion? Okay, so that's where this is going. So, okay, recursive diagrams. I'm going to give an example of what I'm going to talk about, and then I'm going to explain how we basically did this. Okay, so let's focus on the thing on the left here, okay? Forget about this here for a moment. This is a box called R, and it's a family of boxes because it's indexed by a natural number. Okay, so let's look inside now. So the thing to note is we have this thing here, Rn-1. So we're basically recursively using this box inside. And this is, the dividers and the gatherers I draw with this kind of black line. So this is kind of a thing we want to recursively apply on our register. And we're basically just saying, okay, we have this thing, now let's take a wire out and then do the same on n-1. So if we kind of plug in n for 4, for example, we get this thing over there. Yeah, makes sense? Okay, so so these dividers and gatherers in this case are really just syntactic sugar. So you can kind of unfold them out, and this is what you'll get. Okay? And this is all really, I want to talk about this. What are the semantics of these kinds of diagrams, and why would we want these? Okay? So I'm going to give a more involved example, basically, to kind of try and prove why is this useful. So I'm going to show you the Quantum Fourier Transform, okay? And this is it. This is a family of Fourier transforms for any number of n here. So the thing I want to point out here is all the bits in blue and red, they're both just for the recursion, right? So you can build these patterns of recursion that kind of build different kinds of circuits depending on where on the register you go. And the bits in black are just what's needed for the Fourier transform. So rotation in Z and Hadamard gate. And you have this n that you can use around, so you can use the n in the in kind of here in the parameters for the RZ. So it kind of makes it pretty clear what's happening. But this kind of looks a bit weird, and the semantics for these diagrams are things called paramorphisms, which is a kind of a recursion scheme. So you might wonder, why go this roundabout way to make this thing happen? And we do this because the paramorphism comes with certain laws. So you have kind of equations, and you can do equational reasoning between these kinds of recursive diagrams. So I'm going to give you an example. So, this is basically the circuit of the Fourier transform. So we have an embedded domain-specific language in Haskell. So if you build this thing in Haskell, so you can translate the diagram kind of very easily into code, and then you run it, and this generates the circuit, and then this is Kazan basically. You can compile it down to Kazan. Okay, so let's show why is this useful. So I take this QFT and I mirror it, and I can get the inverse basically. So if I get the inverse in the gates in there, and using these laws that I'm not really going to tell you what they are, but I'm just going to show you some examples, I can simplify this further, okay? So first of all, I can kind of drop the blue recursion out, and I end up with this thing. So there's another thing where I can actually drop all of these things, I can cancel out the left and the right, I'm left with this, all Hadamards, and I get the identity. Okay, so we can do these equational reasoning, even automatically in the code, in the Haskell, or you can do it like as pen and paper. And you can see that this kind of makes a diagram, otherwise it'd be very big and willed into kind of something small that you can play around with. And this thing applies to kind of any language based on a symmetric monoidal category. So you can, I've used circuits as an example. You can apply this to ZX or something else. Okay, so how does it work? So we have this, okay. So you give it a monoidal signature, and for our case, we kind of define a type of diagrams, which is just the free symmetric monoidal category. You can drop the symmetry, but you'll need to change some things if you want to down the line. So, or basically, we have a type of diagrams which is just this. So you have a composed, sequential composed, you have a tensor, and these are your types, so the wires and the boxes. We have an empty diagram, and also we have this bottom, because we're kind of lazy, so we're basically kind of a runtime scenario. If you're trying to compose something and it doesn't work, it gives you bottom and say, okay, we're done. Okay, so have people seen this diagram before? No? Okay, so this is a diagram with a hole punched out, basically. We call them cones because you can have as many holes as you want and they kind of look like cones. So I'm going to be using these things. So these things are also kind of the shapes of something called a coend, but I'm not going to even go into that one. But they're also equivalent to a monoidal lens or an optic, if somebody's heard about this. So we basically, and these things form a category, they're morphisms in a certain category, this category optic C. So you basically get a category C, the objects of this optic C are pairs from C, and then the morphisms are going to be these cones. So basically, this is why this notation is here, because this is a morphism from this type to that type, basically. That's why you think of them as functions between diagrams, is because I can plug in a box here, and then this kind of fills up, and I get another box. If that makes sense. Okay. So, yeah, they form a category. This is how we compose them. You can imagine, so the cones, you can build them with these L1 and R1, but like you can just imagine a cone drawn over these things. So you basically stack them like that. Okay? If that makes sense. Okay. I'm going a bit fast. I'm going to slow down at some point, I promise. We can also do the same. So the way I built a type, a set for all the diagrams. I kind of got this category, got all these morphisms, and bunched it in a big bag, and said that's my diagram type, basically. That's all the diagrams that I could have. We're going to do the same for cones. We're basically just a big disjoint union for everything, get them all in a bag. We also tag in bottom and up because we're working in this kind of runtime setting. Okay. So we have these cones, and I said we can look at them as functions between diagrams, and it's kind of pretty easy. It's basically we define this plug, which takes in a comb and a diagram. I'm kind of reverse this here, but like you plug the diagram inside the comb. If it composes, you're fine. You get back your box. If it doesn't, you say bottom, and that's it. Yeah, makes sense. Okay. So, and yeah, you can basically use this kind of. I use this notation like C bar to mean kind of the function between diagrams that you can get from a comb. Okay. Okay, that's one bit over. So now the recursion part. How are we doing recursion is something called recursion schemes. So these are types of recursion. So is anybody familiar with a catamorphism? So if you're not, if you know what a fold is, that's what a catamorphism is. It's just a fold, okay? So you're basically given a non-recursive function here. So this f is an endofunctor, okay? Or you can think of as a data structure. And then this thing tells you how to evaluate one layer of your data structure. So it's not non-recursive thing. And from this you can obtain a recursive function, which is this thing paramorphisms here, which tells you how to now consume recursively your whole data structure down to a carrier type, this thing here. I'm going to give an example. So if I replace f with 1 plus x, its fix is natural numbers, okay? And then I say a carrier type is a string. This is kind of the commutative diagram. So I need to give this thing to convert a natural number to a string. So it just tells me how to peel out one layer of that natural number. If you think of like successive, like, yeah. And then I can consume everything. So as an example, if you can kind of unfold this co-product here, and these are kind of the two things you need to give. You need to give your base case, and your kind of step case where you can consume down things. So here's how it works. So I have a natural number. So the phi 0 is just going to give me my nothing case. Base case, give me 0. And then this is just a function from string to string, my phi star, that kind of wraps around the base case. And in Haskell, it's just this, right? So the phi 0 just gives me nothing. And then this is my phi star here, which is just from string to string. Okay? So it's not really that complicated, although when you think about the categorical semantics, it gets kind of a bit... sorry. Okay. So, okay, for our purpose, we need a kind of a different flavor of this called the paramorphism. So with the catamorphism, you kind of don't have access to the things that were used to produce your accumulated value, right? You can think of this thing consuming down the data structure, but at every step, your function just sees what was kind of passed down before. With the paramorphism, you do have access to this kind of thing. So we're going to use this, basically. And now I'm just going to do the same thing. In our case, we're still using this 1 plus x functor and the natural numbers. Now, however, we're using the diagrams as a carrier type. Okay? So what's happening here is I can get, so I need to obtain this function, okay, this function over here, okay, which given a natural number will give me a diagram. So this basically defines a family of diagrams, okay? But to do this, I need to provide the thing on the left, okay, which is 1 plus d times n, so psi basically. So again, I can do the same thing. I split it into 2. So all that means is I need to provide this phi 0 and psi star, okay? And these are the signatures. So one is just a diagram, my base case, and the other thing is my step case, but in this case, there's an n there. And if you look at the signature there, it's basically an index comb, right? Remember those combs I showed you are functions between diagrams. And an indexed one is just the functions from the naturals to that kind of thing. So given a comb, I can basically make this phi to make my paramorphism. Okay? So that's what we do exactly, is kind of the semantics of this thing is you have this, your diagram over here. This is my comb. So this thing has everything I need, kind of all the work I want to perform recursively. If you imagine my first example where I just have one f that I just applied like this, that's all in there. And the whole is just for the recursion, right? So this is just to show, like this is a stand-in for any kind of diagram that you want to build. And you can nest them, as you saw in the QFT, I had like 2 things nested together. Okay? And usually we take, if you don't provide a base case, it's assumed to be the empty diagram. But then if you do, that's just the paramorphism of kind of your base case and this comb as a function between diagrams. What I want to point out is this box here then, this box is a family of diagrams, right? So you give it a natural number, it gives you a diagram, and that thing is this kind of paramorphism. So that's how you get recursion, and as I pointed out, it's useful because we have these kind of laws that we can play around with the paramorphism, so you can do equational reasoning, and it's much easier to do this and kind of try to do some proofs and like inductive reasoning with this thing rather than we kind of unbounded recursion. So that was kind of the whole point of this. And it's kind of very easy to implement. That's the other thing is, so in our domain-specific language, what we have is the diagrams are basically a big algebraic data type, okay? So you're building your diagrams. So just as you see them, the QFT there is kind of, I'm going to show you because I think I'm going to have time because I sped through this, which probably is not good. Okay, so here's how it works, the paramorphism and the building of this kind of recursive structure. So in here, we have our natural number, 3 in this case. So first thing so the other thing I'm going to point out is, when you look at this thing here, it's recursive. You can see like phi 3, phi 2, phi 1, but the way it's built is kind of from the bottom up. So you kind of start here, you get your base case, which might be the empty diagram, might be an identity, might be something else, and then the phi star will take this, wrap 1 phi 1, and then wrap this in phi2, and this is kind of the index you're keeping. That's why you're using the paramorphism and not a fold, for example, because you are kind of keeping this index around. And the fold is on this type here, right? This is the recursive structure that you're using to build this thing. Okay. So another thing is, if you don't really care about this paramorphism at all, and you don't want to implement this, there's also alternative semantics, where it's basically just a composition of coends, and that's all I'm going to say about this. So yeah, so I showed you these recursive diagrams that you can build. So you can implement this very easily in a language. You also have, with the paramorphism semantics, you also have these kind of coend things that you can do if you want to do category theory. And this is applicable to any graphical language you have on a symmetric monoidal category. And there's an implementation in Haskell. So where this is going is we want to basically try more case studies with this, implement more algorithms rather than just the QFT. You can try Grovers and things like that, and see if this kind of equational reasoning helps you to reason better about these algorithms. Also, you can come up with more kind of useful equations on top of those laws that the paramorphism kind of already has. And then we're going to add this in CHIP, which is kind of a theorem prover for string diagrams that Aleks, my supervisor, is kind of working on. So you can kind of do inductive proofs. This is the end, but so this is basically just to show you just the code, if I had time, this is the code that does the QFT. So these are kind of the patterns, but this is just a diagram. The arrows are just sequential composition, and the ampersand is a tensor product. And you have these diagrams, and you kind of just compose them together and wrap them in this kind of recursive structure. So that's it. Thank you.
Okay, thanks, Zhulien. That's very quick. So we have plenty of time for questions. Start with Mark.
So in all the examples you showed, you have like one recursive call to n-1.
Yeah.
But you could also imagine things where you want to call n-1, n-2 all in the same diagram, something like this. Would you use histomorphism or something like this to express this? Would this be possible?
Yes.
Like Fibonacci, for example.
Yeah, you could try more complicated recursion schemes, but I don't really think they're necessary in this case, because you can kind of, if you want to use different structures, you can kind of wrap dn in some other function that kind of gives you kind of different patterns, if that makes sense. But it's definitely, I've wondered about kind of hylomorphisms. You can do, there's similar work by Mario Roman that does coalgebras, so deals with kind of building things co-recursively, not recursively, where you kind of build streams. So you could kind of think about building something like this and then consuming it down with something like this. But yeah, that's also could be possible with a kind of histomorphism.
Any more questions? Maybe this is too much trouble to do without a board, but could you show an example where the input object and the output object are different? Like a tree.
Yes, you could. One thing you can do is you can kind of forget about, so you could, it depends how you kind of build this kind of recursive structure, that's all. So I can remove all of this, put this box down here, for example, and then that will give me a tensor of these f's, for example. I can kind of build just across any register. So a tree, that's, I don't see, so you don't really have to have this output n here, right? You can remove this and kind of still get a recursive thing that just consumes something down, right? So if you imagine this n, if this f of n didn't have any outputs, if just inputs, for example, or something like this, you can still use kind of the recursive call, if that makes sense. But you can just pad things around with kind of empty diagrams or something like this. But yeah.
Any more questions? Okay, well, thank you very much.
Thank you.